Okay, so as we go through, if you have any questions, feel free to type them in the chat bar, and I will try to get to them as we go through. And if I can't, I'll be able to shoot you an email afterwards. Let me introduce myself. My name's Kevin Lawson. I'm a professional engineer. I've spent about 12 years as a consulting engineer, designing buildings, designing HVAC systems, and left to found Ripple, automating HVAC design. So when you download and install the Ripple HVAC plugin, you're going to have a new tab here, as I'm sure a lot of you are already familiar with. The two new features that are being introduced are AutoZoning and VAV AutoSelect that are here and here. But I do want to point out there is another button that is the help button. And this is just quick links to webinar recordings and articles that you could download, the recording of, how to use the tools, and then the kind of the engineering theory behind those tools. So you all got them nice in one spot right here. So the things we're going to cover today, zoning and VAV selection, the articles are here. And then, the next update, there'll be a webinar recording. This webinar recording will be there. So in order to zone and select VAVs, we need some space data. So if you use the loads toolkit to get your automatic space type assignment and load calculations and CFMs, you'll be good to go to just move on and after diffuser placement, just zone and do VAV selections. If you want to use a third-party tool to do load calculations, the things that you need to import back into the space are your specified airflows. So your specified supply airflow, your specified return airflow, and your specified exhaust airflow. Your design loads. So those would be, let's see. Your design heating load and your design cooling load. So this is going to allow you to select the coil. And your space type. So this is going to give all the ventilation data about your space, because that's what's going to set your VAV minimum. And so in order to select VAVs, what we first have to do is we first have to zone VAVs. And in order to zone VAVs, we have to zone air handling units first. If it's on the same VAV zone, it's obviously got to be on the same air handling unit zone. So if you pop open the user interface for zoning, you're going to see, two rules: AHU zoning criteria and VAV zoning criteria. So it's more important to understand what's going on behind the scenes when you click this button than actually using the button. So I'm going to switch over to a slideshow so we could just discuss what this is going to be looking at behind the scenes and how you zone VAVs. So this is kind of independent of Revit. This is just HVAC design. How do we make rules to feed into a machine learning algorithm that can automatically zone our Revit project? And so let's look into this. So ASHRAE 62.1 really actually helps you define AHU zoning, more than any other standard or code that there is out there. And the way it does that is it separates all space types into air classifications. Class 1 air are things like offices and classrooms. They are, low pollutants, not many odors. You could take that air, you could return it to other offices and classrooms. You could basically spread it all throughout the building, no problem. Class 2, 3, and 4 spaces are higher pollutants. So these are things like exercise rooms, cafeterias, kitchens, things like that. And ASHRAE 62.1 restricts you from taking air from a Class 2 space and sending it to a Class 1 space. This makes sense. You don't want, stinky locker room odor in your offices. It does, however, allow you to up ancillary spaces to class 2. So think about like a gymnasium with a coach's office attached to it. Like that's all pretty much going to have the same pollutant sources. Just feel free to put those all in the same air handling unit. So what are our options if we have class 2 and class 1 spaces like we do in almost every building? Our first option would be to you could still supply the class 2 spaces from the class 1 air handling unit, but you'd have to exhaust the air. And in order to exhaust the air, you're going to have to bring in more outdoor air to make up that exhaust air. So this works, but it's expensive. Outdoor air, you have to condition it, you have to heat it or cool it. It's expensive. So you could also provide a dedicated air handling unit and split these spaces up. You know, class 1 air handling unit, class 2 air handling unit. Now I can return all of this air. The question is just an economics question of when do you provide a dedicated air AHU and when do you provide a when do you just exhaust that class 2 space? So rough calculations, you know, if outdoor air costs, you know, $10 a CFM a year and smaller AHUs cost $10 a CFM, a 4,000 CFM unit would have a 5-year payback. So if you can group class 2 spaces with similar pollutant sources into something over 4,000 CFM, if they're adjacent, then you should probably provide a dedicated air handling unit. If it's something small, like a little kitchenette in a big office, maybe you just exhaust that and not worry about providing a dedicated air handling unit for a little kitchenette. And the way you're going to tell the zoning algorithm that is this number right here, dedicated AHU threshold or minimum AHU CFM. So that's 4,000 CFM. And when the algorithm goes through your building, if it can group any class 2 spaces in the same pollutant group over 4,000 CFM, it's going to assign it to its own dedicated air handling unit zone. And then the question becomes, well, what class 2 spaces have similar pollutant sources? And this is what I've set. So you've got a couple different groups, you know, an aerobics room can share air with a weight room. And this is how you tell it kind of what pollutant groups can be shared. And that's just what these are. So your exercise room is there. You know, dining, things like that. So after we know what can be zoned together, then it just becomes kind of a geometry and economics question. So a couple things to consider when you're zoning air handling units. The larger the air handler unit, the lower the cost for everything, installation, maintenance, and energy. So larger air handling units cost less per CFM than smaller air handling units. There's less filters to change, less motors to grease, less coils to clean, dampers to repair. There's just less maintenance. In addition, large fans are more efficient than small fans, and large motors are more efficient than small motors. So you want to centralize air handling units as much as you can. Another economic is floor space costs money. If you're putting an air handling unit on a floor that could be used for a classroom or an office or a apartment, that's going to cost money. You can think of it as, hey, the owner could be leasing that, or they had to pay for the construction cost, but it costs money. So you want to limit that. And we use ductwork and shafts and piping to put those air handlers out of, out of expensive usable space, and we shift it to rooftops or penthouses or basements or interstitial floors or something that can't be leased out or is less expensive to construct. Third principle is that building height costs money. So the taller the building, the more your facade costs, the more your column costs. There's a lot of cost for every foot that building has to grow. So if the architects want 9-foot ceilings and you need 3 feet of plenum space, like a quarter of the cost of the facade and the columns is really on the back of the MEP trades. So it's important to minimize that plenum space that you need. And this is a constant argument between architects and engineers, but you got to kind of walk a mile in the architect's moccasins, and they're trying to protect the budget here, and so they have to really push you to minimize the plenum space, within reason, of course. So let's take a look at, given these principles, how are we going to accomplish those? So let's look at a building. It's 135,000 CFM, 3 floors, 45,000 CFM on the floor. Let's say it's all an office building or a school. It's all going to be recirculated. We're going to size duct at 0.1 inches per 100 feet. We're going to limit the aspect ratio at 4:1. And we're going to say, at least for the plenum, we're going to have an 18-inch tall duct, because we're probably going to have 16-inch tall equipment in there. Pointless to get it much smaller than this. So let's look at a pretty common way that you can zone air handling units. You could do them floor by floor. If you do them floor by floor, you need a mechanical room on every floor. Okay, that's taking up valuable floor space. In addition, that air handling unit has to serve the whole floor. So you're going to have, when you leave this mechanical room, you're going to have 45,000 CFM in a duct. So at 0.1 inches, that's a 28 by 112 duct. That's a massive duct. Your plenum space is going to be big. It's going to be unwieldy. It's hard to get in corridors. So this is most building height and most floor space. Probably want to avoid this. You can move everything to the roof and get all this floor space back. But again, you still have the problem of you're coming out of this shaft, you've got to get a 45,000 CFM duct out of here. And that's going to be a massive unwielding duct. So the other option is you could split the floor into 15,000 CFM chunks, and those fit in an 18 by 76 duct. So now you've got much smaller ducts that you're trying to distribute through each floor, and you're still get all of the air handling units off the floors. And the way you're going to tell, the algorithm that is maximum shaft CFM per floor and maximum floors per air handling unit. So I have this set to 15,000 and 20 floors. But if you want to do, floor by floor air handling units, you can change this to 1 floor and, 45,000 CFM per shaft, and it's going to zone each floor together. So you can still do that, but you just have to change these two numbers, and that's how you tell it. And the reason we limit it to 20 floors, and this is when you're considering, extremely tall buildings, is as that shaft serves more and more floors, that shaft gets so big that it might be larger than an air handling unit, all together. So after 20 floors, the shaft starts to become bigger than the mechanical room. You got a problem. Now, this normally doesn't happen, but another thing you could do as the shaft goes down floors and less airflow, you could set the shaft back, give the usable space back to the architect and the owner. That's good practice. But a lot of time in high rises, you've got a structural system that makes interstitial floors unusable anyway. So you have a belt wall. You can't put anything really productive in here, so you could put air handling units in here, and then you can, serve down from the roof, serve up from the entry floor or the basement, and put air handling units on the interstitial floors and go down. So depending on the building, if it's a high rise, this number might want to get changed, but in general, that's how the algorithm's going to react. And so the algorithm's going to make a guess on your zoning, and then you could always change it manually afterwards. And we'll go over that in a second. Last point on air handling unit zoning is, all things being equal, try to zone things on an east to west axis. This gives you the most diversity out of your air handling unit. In the morning, the sun's hitting these windows, that's peak load. And it's not coincidence with the afternoon when the sun's over here and hitting these windows. So this is a much better zoning scheme than north to south, where you've got all peak load in the morning on this air handling unit, and then all peak load in the afternoon on this air handling unit. And this is all described in this paper that can be downloaded through the help button here. So you can go back, watch the video, read the paper, go through the presentation, however you need to do that to zone air handling units. So that's what it's going to do in the background. And so I'm going to, I've got my typical 3-story, I think it's about 40,000 CFM a floor, 3-story school here, and I'm going to zone it for air handling units. And so this has to go through and it has to figure out what each space type is, and it's got to build an adjacency matrix to say, hey, what is actually adjacent to each other? What can be zoned together? And then, do it according to the algorithm I just described. Let's finish zoning. Sometimes yeah. So as you can see, it went through. So this is the first floor. It's got a cafeteria. It's got a prep dish. These are on the same pollutant groups. And it's got a storage room. That's a class 1 space that's up because it's ancillary to these class 2s. And it zoned all these together because it was bigger than 4,000 CFM. So it's going to provide a dedicated air handling unit to these spaces. And then there's a cafeteria right above this on the second floor that it's also going to have. So there's going to be an air handling unit, maybe on the roof that has a shaft down to the first and second floor that feeds these, or maybe there's a mechanical room here that it can go in. But it broke the class 2 spaces off and zoned those totally separately. Then it said, hey, to keep your shafts, a reasonable size, we're going to break each floor up into 3 groups because you told me max of 15,000 CFM per shaft. So that's how it broke these up. And those go up the building. So you're going to have air handling units somewhere, mechanical rooms, basement, rooftop, and the shafts are going to feed down to these zones. And again, these can be changed manually. We'll go over that after we talk about VAV zoning. So VAV zoning for schools, it's not very exciting because, every classroom gets a VAV zone. It's much less exciting than an office. So we've made kind of an example office building here that is zoned, like we showed earlier. So for VAV zoning is, a balance between cost and comfort. So if cost is not an object, every single office gets its own VAV, and you've got perfect control, a thermostat in every office, perfect temperature control over every office. Now, and every project cost is a problem, so you typically zone a couple offices together. Now, ideally, when you zone the offices together, the load profile matches exactly. So you've got the same amount of people in the office, they're turning on the same amount of lights, they're using the same computer, they've got the same schedule, and the load profile matches exactly, and there's no temperature drift off the thermostat, compared to the office that has a thermostat that doesn't. Now, in practice, that never happens. Somebody's always out of town. The person with the thermostat's out of town, or and the other office is not comfortable. So that's just a trade-off that you're going to have that we always make. So since we can't match the load profiles exactly, the next best thing we could do is match the loads, within some range. So this is how you tell the algorithm what range you want that to be. So you tell the algorithm, hey, go to all of my office spaces, zone them with adjacent offices, zone a maximum of 3 of them together, and only if their loads are within 15%. So if the loads are in 15%, zone 3 of them together. If they're adjacent, with the exact same space type. There are some other rules like corridors. A lot of times architects will break corridors up into multiple corridors, even if they are one continuous space. So we want to group all those together if possible. And then we just want to put storage rooms just with the adjacent space type. We don't care what the load variance is. We just want to spit a little bit of air into the storage room so it's not, you don't get blasted with heat or cold when you open it. So that is what that's going to be. And these are editable. You can change these if you want to do 4 offices to a zone or 2 offices to a zone, or if you want to, allow the load to vary even more. But that's zone the VAVs here. So that's a lot quicker because it doesn't have to build an adjacency matrix for everything. We'll go to E-zone. Here. And so these are the VAV zones. So, east side, west side, they're going to have, if they're the same size office, they're going to have very similar loads. You're going to group a maximum of 3 of them together. So sometimes it works where you do 3, 2, 2, but I'm not going to zone the corner office with any of these because the corner office has a way different load than these. So that's how it knows, don't zone these 2 offices together because the load's more than 15% different, like we told it. Conference rooms are not offices, so they don't get zoned with offices. Here you can see this office is a little bit bigger. Maybe this is like a VP office or something. I'm not going to zone it with the adjacent smaller office. I'm going to give it its dedicated zone. And because it's got a totally different load profile than the corner office, we're going to keep those separate. So that's how the VAV zoning tool, that's kind of the algorithm behind it. Now, the way you get these, the way the zoning is kind of documented through the Ripple toolkit is there is a text parameter. So there's 2 text parameters. There's Ripple AHU zone and there's Ripple VAV zone. And then to get these color coordinated charts, you just do analyze color fill legend, and you could drop that onto the sheet, and then you could edit the scheme, and then you can make it, air handling unit zone or VAV zone, depending on what you want to see. But the reason we don't use the out-of-the-box HVAC zone for the space is because there is only one HVAC zone. There isn't an air handling zone and a VAV zone, so you got to kind of pick. And so it's easier to just say, just add a text parameter, and that's what will be written. And this text parameter will automatically be added to your spaces when you download the toolkit and run some of the functions. So as soon as you open up the AutoZoning, it's going to import your ventilation calculation schedule, and that's going to have air handling unit zone and VAV zone on it. And that's how you will get to have these parameters. So I highly recommended using these parameters because this is what's going to feed into your VAV selection tool and eventually your air handling selection tool. And again, these could just be changed manually. It's just a text parameter. You can change it with Dynamo. You can change it manually, however you want to see the zone. This just gives you a first pass. Okay, so now we have air handling unit zoning, we have VAV zoning. Let's look at the VAV selection. So before we talk about how we're going to do VAV selection, I thought it might be important to talk about the importance of actually selecting VAVs and why that is getting more and more important. So historically, a lot of firms would calculate the load on the coil based on the air side conditions, and then calculate their water flow, based on that load, write down the GPM, schedule a 2-row coil, and, call it a day. Now, that was never really a problem with high temperature hot water systems. Like if you've got a 200-degree hot water system, a 2-row coil is going to give you so much heat that you're going to be fine. So something's got to float. Either your return water temperature is going to float, or your discharge air temperature is going to float. And what typically would happen is the rep would make all the selections, kind of guess at what you want, and then you could fix it in submittals. Now that still takes a lot of time because you got to go back and forth. But with high temperature hot water systems, you didn't really care what the return water temperature was, because your boiler wasn't condensing. You don't have an efficient boiler. You don't have a heat recovery chiller or a heat pump or anything like that. So it was never that big of a deal. Now with condensing boilers, this push towards electrification, where you want to do a heat pump hot water heater or a dedicated heat recovery chiller, that return water temperature really matters, and getting the right capacity out of the coil really starts mattering. Not to mention, a 2-row coil might not work, might not give you the capacity you need. And then, hey, is it a change order if I have to go to a 4-row coil? And what's the GPM that I need? Like, because I'm sizing a pump or sizing a boiler on this. Like, what is actually going to be happening when I'm in full heating mode? So it's just good to get a good selection on VAV coils. So you can go through this, how this actually works. The coil conditions have to be satisfied. You got to let something float. Typically what you let float is your outlet water, because for the boiler doesn't care if it's 100 degrees or 98 degrees or 95 degrees. It's going to be condensing in any of those ranges. And once these all mix together, it's going to be, something kind of different. But you do care about the discharge air temperature, because ASHRAE 90.1 sets limits on that. So that's why you should be selecting VAVs. And then again, now that this is automated, it's much easier to do. So we're gonna pop open the VAV AutoSelect tool. And what this is really is, this is just a manufacturer's, its prices VAV selection tool just built into Revit. So that way it could take your data from your spaces, calculate everything you need, automatically talk to prices VAV selection tool online, pull back the right sizing information, and drop the right family into your project, so you know right away what size VAV you need, how many rows it is, what the GPM is, what the neck sizes are, what the outlet sizes are, and you could go and start getting a real design much faster. So in order to do that, you need space data, the space data we talked about, your airflows, your loads, and your space type, because your ventilation data is necessary for the minimum. And you need some additional data. And this is where that additional data is put in. So, hey, what do I want? Do I want hot water coils, or do I want electric coils? So let's assume this is hot water. Do I want to provide reheat coils on internal zones? So I've always provided reheat coils on internal zones, because the VAV minimum is driven by ventilation, not driven by thermal load. So you might be supplying a lot of really cold air and freezing people out if you don't provide at least a small reheat coil. Your zone air distribution effectiveness is going to set your VAV minimums in heating mode and cooling mode. So you need to give that information. So 0.8 and 1 is typical for that. you might want to override the entering air temperature. So if you're doing like a supply air reset off your air handling unit and you're resetting it to from 55 to 65 and you want to size your VAVs there, you can override that here. Otherwise, it's going to size them at, the information on your space. Where do I want the VAVs dropped in? The VAVs are just going to be dropped in on top of the space at this height, so 8'6". Demand control ventilation. Now this matters because the thermostat that if you want to schedule a thermostat with your VAV, you're going to want to schedule a CO2 sensor. And sometimes in demand control ventilations, you want to reheat. So demand control ventilation is going to decouple your VAV flow from your thermal load. So if you have a lot of people in a conference room, but it's really cold outside, so there's not a lot of load in that space, you might be going to full cooling, but there's no need for cooling. So you might be freezing people out there too. So you might want to reheat that whole max flow to neutral, and that affects your coil selection. So that gives you an input there for that. Then it's just back to general, how do I want to select these? So maximum leaving air temperature is 90 degrees. Now this comes from 90.1. It doesn't necessarily mean that the VAV is going to be selected at 90. It's just this is the maximum it's going to be. So if 85 degree satisfies your heat load, then it's just going to size the coil at 85, not 90. Now, if you need 95 at your ventilation minimum, it's going to say, hey, my reheat minimum is actually higher than my ventilation minimum, and it's going to figure that out for you. And there's some helpful tool tips here. When you hover over it, you're going to get some information about what all the parameters are. Maximum assembly air pressure drop. What is the limit of how much air pressure drop I want to take at my VAV? Typically, it's a 1/2 inch. If it gets any higher than that, you're going to upsize the coil, or you're going to upsize the neck size or the coil size, or the coil casing size. What is my minimum air velocity pressure? So this is going to come from the controls contractor, and this is what the absolute minimum the VAV can control to. And if that's under your ventilation minimum, hey, no problem. What's my water pressure drop? Maximum water pressure drop, 5 feet. If it gets over that, you're going to upsize the casing. What's my heating water supply temperature? And what's my either delta T or my maximum return water temperature? So I've got a condensing boiler. I'm supplying 125 degree water. I want 100 degree water back. I can't set what this is exactly. So this is just going to increase coil rows until I get to at least this. So I might get 95 degree return water temperature. It's just going to be something more than this. Now this is all well and good, but sometimes, especially if you're doing reheat coils on internal zones, you might have just a very, very small water flow, and you don't want to put a 4-row coil in just to drive this delta T so high when you've got very little GPM. So there's ignore delta T requirements under flow. So if you're just a 1/4 GPM, you're just going to put the first coil that meets capacity in there and not care about the delta T. Fluid type, in case you've got glycol, your liner, and then this is all sound information. So what liner do you want? And again, these have full tips on what they are. What you're assuming the inlet pressure is, what you're assuming the outlet pressure is, and then what your max NC is. Now, typically, the NC is not going to drive. If you're picking a good liner and picking a reasonable pressure drop, the NC isn't going to drive the size of the box. The size of the box is going to be driven by the pressure drop. So it's good information to have, and the information is going to, pull forward to the VAVs. But this is just here in case maybe you want to allow a really high assembly pressure drop. And then there are some kind of preferences. Oversized casings. So you can ship like a 8-inch neck with a 10-inch casing coil. That allows you to reduce the minimum airflow on your VAVs while still getting the larger coil capacity and the lower pressure drop. So I recommend leaving this checked. And high capacity coils just go from 10 fen per inch to 12 fens per inch. I recommend leaving that checked too. I don't see why you wouldn't allow that. And then even sizes only. So they, you can get a 5, 7, and 9 inch. And I think 5, 7, and 9 inch is great because, again, smaller neck size, lower minimum. No reason not to. Even if your contractor wants to do like a 10 inch out, it's just a reducer to a 9 inch. Not that big of a deal. And so if you're familiar with VAV selection, this should kind of look pretty familiar to you. The tooltips help give you a prompt as to what it is. And if you really want to dig into the details about how all of these are set and what is calculated, there's the definitive guide to VAV selection. This is going to be published in June, and I can send you guys a link to it. You can also download it. Help definitive guide to VAV selection article download, and it's going to tell you, what's the VAV controllable minimum? How do you calculate that based on your inputs, your ventilation information, neck size, noise criteria, how the heating coil selections go. We haven't talked about electric yet. Liners, CO2 set points. All of this information is kind of written up in here, and then it gives you kind of a schedule on how all of these things are calculated and what they are. So this is really helpful to refer back to. Okay, so the other thing is, so this is for hot water. Electric is a lot more simple. You still have some maximums that you want to maintain, but all the heating water stuff is out of here. You just have to pick your power supply system and how do you want to control it. 480, 277, or 208, 120, 240, 120. And then what are the breakpoints you want to, where do you want to select these VAVs? So this is probably a conversation with the electrical engineer on the project. Do you want everything to be at 3-phase? If that's the case, you can, make these not selectable and everything will be at 3-phase. Do you want to use single phase 277, but not single phase 480? Then you leave this, and anything under 4 kW is going to be selected at 277. But that's electric. So let's assume hot water, and that's batch select these. So what this is going to do is it's going to follow, the procedure described in this document. It's going to take all your space data, your loads, your ventilation information, your airflows, and it's going to call up to Price's online selection software, select the VAV, and then drop the family into the project. So all that takes, a little bit of time. But then you should have the VAV selected. And these are going to be based on your VAV zones that are, so your 2 offices are on the same zone as dictated by the text parameter. It's going to, add those airflows up, add the, heating loads up, figure out what the required discharge air temperature is, and make the selection and drop it in the project. So let's see. Okay, so. And it's going to, like I said, it's going to drop the VAV. So this is a project that the VAVs have been selected on. It's just going to drop the VAV at 8'6" above the space of the zone. And then it's going to create, all of these have schedules. It's going to write a ton of good data to the VAV. So this is a VAV schedule. And it's going to write the area served from, the space name. So you don't have to copy all this stuff into an Excel. You don't have to manually do that. It's just going to take the space names that were zoned together and write them here. Your inlet size, your casing size, your weight, how the controllable minimum is calculated, how all your ASHRAE information is calculated, what's your area component of your breathing, what's your population component, what's your ventilation effectiveness for both these. And from that, it's going to calculate what your cooling min is, what your cooling economizer minimum is, what your heating minimum is, how much reheat do I need, what is the leaving air temperature, how many rows do I need? So some need 3 rows, some need 1 row, some need 2 rows, but you're getting a real coil selection. What's my actual leaving water temperature? What's my actual pressure drop, both in water flow and airflow? Coil handing is going to follow the actual family. So if I go here and I say, I want a left-handed coil, the coil is going to flip, and then now I'm going to get a left-handed coil here. So your handing follows what you design automatically. So this makes the middle review much easier. Your actual noise criteria comes through. So here's what the maximum was set at, based on the input. Here's what it actually came out to. And this is kind of why I know that if you set your pressure drop reasonably, you're not really going to get close to your discharge NCs. And then all your octave band information is in there. Additionally, depending on the space type, what do I want my set points to be? What do I want my sensor types to be? If it needs demand control ventilation, what should the CO2 set point be? It just brings a ton of good information out of your space and into the VAV, so you get a really complete schedule. Now, you probably would never put this schedule on a set of plans because it's just way too much information. So what I would do is I would just duplicate this schedule and then delete what you don't want to show. Maybe you don't want to show acoustics data. You could just hide that or move it. If you want to change like what your set points are or what your sensor type is, a lot of that information comes from the space type additional data schedule. So here are all your ASHRAE 62.1 space types. Here's my default cooling mode set point, unoccupied cooling mode set point, heating mode set point. What kind of thermostat do I want in there? What my exhaust rates are, what my metabolic activity factor is for each space type, so you can calculate the CO2 sensor. So a lot of good data goes into to these. Same goes for the electric coil. Electric coil looks very similar, except for there's no heating water information. There's just electric information. Another feature of this is that in order to select these VAVs, you have to do the ventilation calculations on a space-by-space basis. Now, spaces are kind of frustrating to design with because you as the mechanical, you own the space, but the architect owns the bounding element. So as the architect is deleting walls and then replacing them or getting rid of them altogether, your spaces might get blown away. So it's frustrating to have a bunch of data on a space and then it gets blown away and you got to remake the space, get the data back in there. So what this does is it takes all of this information from the space that is used to select the VAV and pulls it up into the VAV. Because you own the VAV, the architect's never going to actually accidentally delete the VAV. And so that's what this price VAV ventilation schedule is. This is a VAV schedule, but it's got all the zone information copied to it when it places. So you've got the area, the outdoor air rate, the population of it served, the ventilation rate per person, what that information is. It's got the zone ventilation effectiveness from the VAV selection user interface, and then how all of these, all of the airflow set points for ventilation. And again, that's all calculated based on this, which is according to ASHRAE 62.1 and then ASHRAE 36. So that way, now it doesn't really matter. So if your space is starting getting deleted, you have all of the information you need for a ventilation schedule on your VAV. So yeah, so the goal there is, I understand how frustrating it is to keep spaces in and keep them up to date. But if you use the Ripple toolkit, get your spaces placed, get the data in there, get your air terminals placed, get your VAVs placed. Now you don't need your space anymore. So the architect can mess with your spaces as much as you want. You've got all the data you need in a short period of time. So you only have to keep these active for one session, hopefully. Another thing to point out is if you have a huge space that's, one zone, it might need 3 VAVs. So you're not going to get 11,000 CFM VAV underneath a ½ inch. So it's going to figure out how many VAVs it needs, and it's just going to renumber these 0.1, 0.2, 0.3. So this was zone 3-1. So this is equipment 3-1, 0.1, 3-2, 0.2, 3-3.3. So that's the VAV selection. So this is, I have spent so much time selecting VAVs that to have this really quickly in a couple minutes is, man, this just saves so much time. And that's why I was really excited about the VAV tool and built this. The next tool to come out, so we've already got our air handling zoning in. So we're going to build a very similar interface to the VAV AutoSelect tool. It's just going to be an air handling AutoSelect tool that's going to follow very same procedures based on the very same data that you have here. All your ventilation data, all your CFM data, your VAV minimum information is now in the model. So it's great to get here, but getting here and having all this data in and right can propel you forward towards the next level. So that is the VAV tool. I wonder, let's do electric too. I'm sure I'm missing something, and I know I've got a lot of questions, so I will follow up by email. Okay, so that went through and that selected the VAVs based on this criteria, and it just dropped them in. So now I've got hot water coils and electric coils just sitting on top of each other. And now my electric coil is filled out. So you can see here's the heating capacity, and if it's over 4 kW, it's going to pick 483 phase. If it's under that, it's going to pick 277 single phase. The control is all going to be SCR. Same thing. The handing follows what you have designed. That'll help some middle time. You have all of this, same data that you had on your reheat in there. Okay, so that's the tool. Again, free of charge. Download it, give it a try. Let me know what you think. I'll put together this recording. I'll email it to you all along with the zoning slides. So if you want to sign off, I can email you the recording, but I'm just going to try to go through some questions so I can get a jump start on these. So the CFM chunk is sum of zone peaks. So it will, these are these are broken up into 15,000 CFM chunks based on specified supply airflow. Okay, can you go over how views are set up, auto populates, or do you need to create? Yeah, so the views are built in. This is just built-in Revit functionality. It is the analyze color fill legend. Now, the color fill legend is based on a ripple parameter, ripple AHU zone or ripple VAV zone. Oh, let me share my screen. Sorry, guys. Okay, so these are these views. To get these views are very helpful. Early design review with owners and things like that. It's very useful to go over air handler zoning and VAV zoning. So this is just an out of the box color fill legend that you drop here, and then you set the scheme based on the zone, the ripple AHU zone or the ripple VAV zone. So that's out of the box. Now the parameter it's based on is going to come with this schedule, your space ventilation calculation schedule. It will, when you open the AutoZoning tool, it will check to see, do I have this schedule? And if not, it will import it. And when you import it, it will add these parameters to your spaces. So that's all automatic. You should be able to just open it up, hit zone, and it'll zone, and you can create these color fill legends. And like I was saying, you could zone these manually too. So you could run the auto zoning, and if you hate it, let's see, you can clear all the zoning. You can manually change it. Like I changed these from air handler 1 to air handler 3. You just have to select the spaces, and you change this parameter. So I'm going to change this back to 1. And then it's going to show it as a separate air handling unit. For hospitals, this is really intended. So a question is about hospitals for zoning. So I don't have ASHRAE 170 space types built in here yet. That is something that's on my to-do list. There's just a lot of other rules that need to go into hospitals that I kind of want to wait till I'm a little bit farther along before I go back and address. So you can use this for hospitals, but it's going to be a little bit more difficult You're going to have to make your own space types and make your own zoning rules for those space types. Yes. So you, just like for the automatic diffuser placement, the families that get placed, they have to be the families that come with the toolkit, because I have to know what parameters map to what selection parameters. But you can add parameters to the schedule however you see fit. And you can hide parameters from the schedule. You can modify the schedule however you see fit, just by opening the family and editing it like you normally would. So right now, the question is, does the tool only work for the entire building, or can you do this floor by floor? So right now it only works for the entire building. And then again, you're back in manual mode. You can go floor by floor and rezone as necessary. Can the price families be swapped out for other manufacturers? No, they can't. So again, the price families have the specific parameters necessary to access the online selection software from Price. So any other manufacturer, I don't know what their parameter name would be for leaving air temperature to go and select, and then plus they don't have an online selection software, so there's nothing to really call there. So it's really it's price families that are the only thing that's going to work here. Okay, question. ASHRAE 36 for ventilation parameters should be group heading to 60.2.1. Yes. Okay, so the question is, the ASHRAE 36 heading for these parameters should be named 62.1. Yes, that is correct. So these are the ASHRAE 62.1 variables, or the ASHRAE 62.1 settings. Now, ASHRAE 36, the way they kind of describe doing the minimum airflow calculations is they leave that to the controls contractor, and they tell the engineer, hey, provide these values, and we will calculate, and the controls contractor will calculate these values. So that's why it's titled ASHRAE 36. So I'm kind of a fan of calculating these airflow set points, and then just giving the controls contractors the actual CFMs I want programmed, as opposed to trusting them to calculate based on these. But I put them both here because I assume you're going to hide one. So if you don't want to schedule these, if you're used to scheduling airflow set points in CFM, you can do that. If you want to follow ASHRAE 36, you can hide these and just schedule those. So I'm just throwing a ton of information at you and letting you see what you want. But that's why it's headered as ASHRAE 36. Okay, another question. Does ventilation parameters understand their multi-breathing zones and using multi-zone recirculation system calculations? I guess since you're using ASHRAE, that it uses Appendix A at all times. So the way that these are calculated, these airflow minimums are calculated, is based on the ASHRAE 62.1 simplified minimum flow calculations, which basically just says 1.5 times your humidity, or 1.5 times your ventilation requirement in that zone. And this is what ASHRAE 36 follows too. So if you were to just give your contractor these variables, your breathing zone area, breathing zone population, and your effectiveness, that's how they would calculate it. So that's what these are based on. It's based on ASHRAE 36 using 1.5 times your ventilation minimum in cooling and heating mode based on your ventilation effectiveness. Okay, another question. Are you going to be partnering with any air handling manufacturer in particular? I haven't reached a decision on that yet. So more to come on that. We develop a tool for constant volume systems. Yeah, so a tool for constant volume selections. That I believe I will address that when I get into hospitals and laboratories, things that are air change driven as opposed to ventilation driven, where you do want, constant volume airflow regardless of, what the ventilation minimum is. So not at this time, but in the future. All right, I think I got to most of them. I will be making a presentation at the ASHRAE conference in June called AI in HVAC Design. If you guys are in Tampa in June, come see me, come say hi. Feedback's always appreciated. Feel free to shoot me an email, and check your email in the next couple of days for this video and the rest of the presentation. All right, thank you very much.